Hello everyone, my name is Oindrila Ghosh. I am a fourth year PhD student in environmental engineering at the University of Maryland, Baltimore County, United States. Today I am going to present my work on a mathematical approach to interpret time integration in equilibrium passive sampling. This work was done in collaboration with my colleagues at UMBC, Dr. Songjing, Dr. Mandar Bokare, and my PhD advisor, Dr. Upal Ghosh. I would like to thank the DoD SERDIP program for funding this project. Hydrophobic organic contaminants like PCBs and PAHs have strong bioaccumulation potential and persist in the environment long after their use has been discontinued. They keep partitioning among the different environmental phases. Using passive sampling, we are able to measure the freely dissolved concentrations of these HOCs, which is the thermodynamic driving force for their biouptake. Passive samplers also provide a time-integrated measurement of the concentration levels at a site, which is important for ecological exposure assessment. Passive samplers accumulate contaminant compounds into the matrix of the polymer following a first-order kinetic path as shown by the bold black curve in this diagram. Samplers are classified as kinetic or equilibrium types depending on the accumulation stage reached during the deployment. Closer to equilibrium, the changes in kinetics do not affect the mass transfer of hydrophobic chemicals into the sampler. So at that point, the freely dissolved concentration in water can be directly linked to the concentration in the sampler by a simple partitioning coefficient. Polyethylene is one of the most used equilibrium samplers for HOCs like PCBs and PAHs because it has a simple chemical makeup that makes its analysis less complicated. It is often possible that passive samplers do not reach a state of equilibrium in practical deployment times, and in that case, a correction for equilibrium is required. So passive samplers are preloaded with a known concentration of performance reference compounds which have similar diffusivities and partitioning properties and therefore face identical mass transfer resistances as target analytes. So at any given point of time, the fractional loss of the PRCs from the sampler to the ambient medium can be used to correct for non-equilibrium conditions and calculate the water concentrations using the right partitioning coefficients. In the field environment, events like storm flow, industrial runoff, and tides often lead to the temporal variation in the ambient water concentration of HOCs. One of the important advantages of using passive sampler is that it provides time-integrated measure of the contaminant concentration at a site. But to accurately estimate the true time average concentration, we need to have some knowledge about the accumulation mechanism of contaminants of interest within equilibrium passive samplers, the surrounding medium, and the environmental conditions. There are two main mathematical models that are used to analyze sampler water exchange kinetics, the diffusion model and the first order model. So the second knowledge gap that we try to address here is compare these two models in understanding the mass transfer kinetics in a single phase equilibrium passive sampler like polyethylene for time integrative measurement of surface water concentrations. I will now explain these two models in detail, and I will use the example of uptake or loss of PCB compounds into a polyethylene passive sampler. In the beginning, we are not sure about which side controls the exchange kinetics of a PCB compound between the sampler and the water. In such scenarios, when we do not have a very robust mechanistic understanding of the exchange kinetics, we use a diffusion model. So in the diffusion model, we assume that there is a diffusive water boundary layer on either side of the sampler. What you are seeing here is essentially a cross section where we see half thickness of the sampler and the water boundary layer associated with that side. We apply Fick's second law of diffusion to both the sampler and the water boundary layer and use these governing equations that you see here to analyze the concentration profiles within each side, the sampler and the water boundary layer. We use a numerical solution of the diffusion model here because we intend to use this model for assessing impact of fluctuating ambient concentration later on. The first order model assumes that the exchange kinetics can be approximated as a first order process. So the rate of uptake of chemicals in the first order model in the sampler is a result of competing uptake and elimination processes. So here we assume that the rates of absorption of the target compounds and desorption of the reference compounds are equivalent and can be represented by an overall exchange rate coefficient Ke, which can be empirically measured. The research objective is thus to develop the modeling framework of exchange kinetics in equilibrium passive samplers when there is perturbation in the ambient concentration. We specifically look at the exchange of PCB molecules in a PE sampler here. The knowledge gaps that we address are the theoretical understanding of mass transfer in polyethylene and confirm the consistency of the diffusion and first order models. Through the mathematical modeling simulations, we study the impact of the timing of the perturbations, hydrophobicity of the PCB compounds, and the sampler thicknesses on the final measurement. In each case, we compare the passive sampler predicted concentration with the actual time averaged concentration, and finally compare the predictive accuracies of the diffusion and first order models to identify any underlying cause of inconsistency. As a first step of setting up the mathematical model, we use the diffusion model to simulate the fractional loss of an analyte from the sampler to the water, assuming that initially all the chemical is in the sampler, and on the water side the concentration is 0. Parallelly, we simulate the fractional uptake of the same analyte from water to the sampler, assuming that initially all the chemical is in the water side and on the sampler concentration is 0. From the first simulation, we get the fractional loss of PRC term at the end of the exposure time, and from the second simulation, we get the mass of target analyte accumulated in the sampler. From these, we can calculate the corrected water concentration at equilibrium using the right partition coefficient. For the first order model, the mass transfer coefficient is proportional to the natural log of the ratio of initial and final PRC concentration in the sampler. Since this is a modeling experiment, we derive this ratio of PRC concentrations from the diffusion model to calculate the Ke term, and from there we calculate the water concentration using the right partitioning coefficients. Since we are comparing the passive sampler predicted concentration by these two models with the actual water concentration, we calculate the actual water concentration using this equation right here. In real deployments, we usually expose our samplers for about 60 to 90 days. So for our modeling experiments, we assume that our total exposure time is 90 days. For the first set of results, we are looking at the impact of timing of perturbation on the uptake of PCB37. For this, we considered the nature of the ambient surface water perturbation to be a 10x dilution pulse that lasts for 10 days. It's important to mention here that though we are looking at this specific kind of fluctuation, the advantage of using the proposed modeling framework is that because of the numerical solution used here, we can incorporate any pattern of fluctuation or perturbation. The plot on the left shows how the actual water concentration varies with time and under no perturbation scenario. And on the right plot, we have the pulsed perturbation starting on the 10th, 50th, and the 70th days, represented by the different dashed lines. So when the perturbation hits, the concentration goes down from 10 nanogram per liter to 1 nanogram per liter, and then back to 10 nanogram per liter post the perturbation. So since the actual time averaged concentration depends on the period of the perturbation lasting, which is 10 out of 90 days, Regardless of when the perturbation starts, this concentration stays constant at 9 nanogram per liter. In comparison, here we are looking at the accumulation profiles of a tri-homolog compound PCB37 in a 1 ml PE passive sampler under no perturbation scenario on the left and under the influence of the perturbation scenario starting on the different days on the right. The passive sampler predicted dissolved concentration is plotted against the starting days of the perturbation in this bar plot here. The numbers marked in orange are the fractional accuracy terms, which is the ratio of the sampler predicted and the actual time averaged concentrations. So when the starting day of the pulse moves closer to the 90th day, which is the end of the exposure period, the effect of the perturbation is very freshly felt by the sampler and we end up underestimating the actual time averaged concentration. But as the starting day of the perturbation moves farther away from the 90th day, the effect of the perturbation felt by the sampler also fades away until it almost seems that the perturbation never happened. So a crossover happens from being over-predicted to being under-predicted, and for PCB37 it happens around when the pulse starts on the 60th day. So the time period of integration, which is the number of days required to safely predict the true time average concentration for this compound, is about 90 minus 60 or 30 days. There is yet another term that I want to draw your attention to, and it will get a little more relevant in the next couple of slides, which is the degree of sensitivity or the percentage crossover term. It is a measure of how much the predicted concentration is influenced by the ambient perturbation for a PCB compound. And it is calculated as the sum of the percentage deviation of the predicted concentration from the actual time averaged concentration around the day of crossover. So for PCB37, it is calculated to be around 6%. Next, we want to look at the impact of hydrophobicity of the analytes on the diffusive uptake in the same 1 ml PE. For that, we are looking at a list of 4 PCB congeners here that are listed in ascending order of molecular weight and hydrophobicity, represented by the octanol water partitioning coefficient. When there is no ambient concentration fluctuation, for the lower congeners, they reach equilibrium much faster than the higher congeners. PCB4 here, for example, which is represented by the red solid line, reaches equilibrium in less than 10 days, while PCB128, which is represented by this green line, has reached only 25% of the actual ambient concentration in 90 days. When the dilution pulse hits on the 20th day, the lower homologs appear to be much more sensitive, undergoing a much deeper dip as compared to the higher homolog compounds. In this bar graph, we plotted the equilibrium concentration predicted by the passive sampler when the perturbation moves closer to the end of exposure period for the different PCB compounds. The lightest gray bar corresponds to when the pulse was hit on the 70th day, and the darkest gray corresponds to when it hit the 10th day. We see that for a tri-homolog like PCB22, when the pulse starts on the 50th day, which is the intermediate gray bar, concentration is over-predicted by about 8% versus when the pulse starts on the 70th day, it is under-predicted by about 12%. For PCB128, because it is more resistant to diffusive fluxes, the percentage of over or under prediction of water concentration is quite low. We further correlated the time period of integration with compound hydrophobicity or log KOW and represented the degree of sensitivity of a compound with the radius of the bubbles. We see that while a compound of log KOW, say 4.5, requires only 2 weeks to recover from the pulsed perturbation and is very sensitive, a compound of log KOW, say 6, needs at least 36 days and is about 94% less sensitive to the ambient perturbations in concentration. Finally, we look at the impact of sampler thickness on the uptake of PCB37. For that, we are looking at the fractional uptake of PCB37 in PE sampler of varying thickness from 0.3 to 3 mil. And we see that when the pulse perturbation starts on the 70th day in ambient water, PCB37 reaches equilibrium slowest and experiences the least sensitive dip due to the pulse for the thickest polymer, which is represented by red here. The correlation between sampler thickness and time period of integration with the degree of sensitivity represented by the radius of the bubbles. As before, we see that the thickest polymer is most resistive to the perturbation in the ambient concentration as compared to the thinnest polymer. So using a thicker polymer would need more PRC correction and can be a source of error. So passive sampler thickness is something that will have to be optimized for the right cause. For example, if we want to do short-term deployments and aim to capture the input from an episodic event, using a thin polymer might be more advantageous. The final aim of this work was to look at how consistent our results were across the two models. For this, we are looking at a surface plot where the x-axis corresponds to the starting day of the perturbation. The z-axis corresponds to the log KOW of the PCB congeners. The y-axis corresponds to the percentage accuracy. So we get a three-dimensional surface curve, which is a function of these three parameters and consequently is a measure of the sensitivity of the compound sampler design system. And the shape of the curve essentially gives us an idea about the sensitivity of the system to the perturbation scenarios. So first, let's look at a case we have already seen before. For lower KOW values, when the starting day of the perturbation varies from 10 to 70, the percentage accuracy varies from about 110% to 10%, and the curve goes from green to dark blue. With increasing hydrophobicity of the compounds for the highest KOW values, the accuracy term goes from about 100% to 90%, so the curve goes from green to the lighter blue. So this essentially shows how sensitive the compounds are to the perturbation. There is higher variability for the less hydrophobic compounds, more variability for the less variability for the more hydrophobic compounds. When we compare these plots for a 1 mil PE versus, a 0.3 mil PE versus a 3 mil PE as observed with the diffusion model, we observe that there is an increased sharpness of the pointy edge of the curve. And this happens because with increasing thickness of the polyethylene, the sensitivity of the system reduces. We generated the same surface plots with our results from all the above scenarios using the first order model for the 0.3 mil PE, and we observed that the diffusion and the first order models produced very similar results. In conclusion, we could establish that the minimum amount of time that is required by a compound to represent the true water concentration, which is also the time period of integration for that PCB compound, is dependent on the nature of the perturbation, the hydrophobicity of the analyte, and the design of the sampler. For a 10-day long pulsed perturbation, the range of time period of integration varied from 14 to 15 days for a dihomolog to about 43 to 45 days for a hexahomolog PCB. We also established that both the diffusion and the first order models created consistent predictions of the true water concentration under perturbed scenarios. There are certain assumptions that we need to keep in mind. First is that the real-time perturbations last only for a couple of hours. So what we are looking at here, the perturbation that we modeled was definitely an exaggerated form of perturbation. That being said, it is important to mention that since we are using a numerical solution of the diffusion model here, any pattern of perturbation can be incorporated into this modeling framework. Also, there are always errors associated with PRC corrections for a higher homolog or a thicker polymer, or even calculating exchange rate coefficient. Um, the interpretations made in this study can be further utilized for optimizing the choice of passive samplers to make accurate surface water or sediment pore water measurements based on the site, the compounds of interest, and the desired exposure time. With that, I would like to thank you, and I can take any questions that you might have for me.